Welcome everyone. My name is Stepankin. In this session, we'll dive into mTLS and authentication based on certificates. I'll explain some interesting attacks on mTLS, as well as demonstrate vulnerabilities in popular open source software. My purpose is to give you some fresh ideas on how to attack and secure this technology. So, what is mTLS? In short, it's another form of client authentication. Most of you probably know that the browser checks the server certificate before sending any data to a website. The same idea can be applied to authenticate browsers or TLS clients in general. For example, a server can ask a browser to provide a valid certificate. It can either be used as an alternative to classic password authentication or as an additional factor. This process is defined in the TLS RFC and based on asymmetric cryptography. During the handshake, the server can send a certificate request message. The client replies with a certificate message with a public key. This is followed by certificate verify message encrypted by a private key. It sounds complicated, but so that even if the message is intercepted, a person in the middle would not see any secrets in the plain text. As you may ask, how does the server check that the client is authorized to establish this connection? It does it by requiring a client to present a public key in the form of a signed certificate. So, what exactly is a certificate? Generally speaking, it's a blob of binary encoded data. The most important fields are the subject, the issuer, and the public key. Subject usually defines a username or host name. Similar to JSON Web Tokens, the certificate is signed by the issuer's private key, so the data inside cannot be tampered with. The issuer field points to another certificate who signed this certificate. A sequence of certificates assigned each other to the trusted root forms a certificate chain. In order to check the validity of the certificate, the server should build a trusted chain from the client certificate to a trusted root certificate. The client and intermediate certificates are normally sent by the client, whereas the server only needs to know about trusted root certificates. So let's see how to use mTLS in a Java web application. In the bare minimum, the developers only need to enable it in the application settings and specify the location of all trusted root certificates. From the client, such as curl, you need to specify what certificate is sent to the server. The rest of application code, such as request mapping, is exactly the same as for normal web applications. As you can see, this approach brings some advantages and disadvantages compared to traditional authentication methods, such as passwords. So first of all, it might be faster for your application as the authentication check only happens at the handshake level, and all subsequent requests will be authenticated, saving our CPU time. Also, similar to JSON Web Tokens, there is a storage benefit, as a server does not need to store all the certificates, only the root certificate. Speaking of the cons, there is no granular control. As soon as you enable mTLS in your application, all requests have to be authenticated, even to the public pages or JS or CSS resources. Also, any certificate signed by a root certificate can be used for client authentication. Even if the certificate is issued to a different purpose, it can still potentially be used for TLS authentication. Furthermore, the mTLS RFC does not require how certificates should be issued. It's up to application developers to design mechanism for the certificate issue. Finally, certificates are always expired, and just to hassle to rotate them frequently. Well, before we dive into the attack section, I'm going to briefly mention the previous well-known attacks on certificate validation. Obviously, the security of the authentication system depends on the strength of the signature. If we can somehow forge the content of the certificate, but keep the same signature, we can completely break the authentication process. Also, since the X509 format is quite complex, just parsing these data structures can lead to buffer and heap overflows. In addition, lack of basic constraint checking can also be used to bypass authentication. I have to say that in my research, I mostly looked at how mTLS is implemented in applications written in Java. In the Java development kit, most of these attacks are already mitigated, so I had to take a slightly different approach. At the same time, all the attacks I'm going to describe are also applicable to other languages. So let's move on to the attack section. In the first chapter, we'll cover some improper certificate extraction. In real-life applications, developers often need to access the subject name from the certificate presented during the TLS handshake. For instance, they may need it for authorization needs to understand what is the current username. In Java, you can use SSL session.getPerCertificates method. Interestingly, this method returns an array of certificates, not a single one. Why? Perhaps because TLS specification defines that clients may send a full chain of certificates from an entity to the root CA. So I decided to take a look how different applications use this API. The most common approach I've seen is to take only the first certificate from the array and consider it as a valid client certificate. This is correct, as mTLS RFC explicitly says that the sender certificate must come first in the list. At the same time, I discovered some rare cases when applications disregard this rule and iterate over the array, trying to find a certificate that matches some criteria. This can be dangerous, as the underlying TLS library in Java only verifies the first certificate from the list. One of these examples was a vulnerability I discovered in Keycloak. Keycloak is a popular authorization server that supports OAuth, SAML, and other authorization methods, as well as mutual TLS. Keycloak iterates over all certificates in the array, searching for the one that matches the client ID form parameter. As soon as it found one certificate, it implicitly trusts it, assuming that the signature has already been checked during the TLS handshake. In reality, a client can send as many certificates as they want, and the server only verifies the first one. A potential attacker can exploit this behavior to authenticate under a different username. It is possible to send a list of certificates where the first one contains one username and properly chained to a root CA. The last certificate might be self-signed and belong to a different user. The client does not even need to provide a valid private key for it. There is a number of endpoints in Keycloak that support mTLS authentication. For exploitation, we need one that does not require any additional factors, such as tokens or secrets. Client management register node is a good example, as it mutates users' data. In the first command, it's shown how we can normally use this API with mutual TLS. In the second request, we can generate a new self-signed certificate using OpenSSL and add it to the chain. When we send the second curl request, Keycloak will perform this action on behalf of the user specified in the certificate 2 instead of certificate 1. Therefore, we can mutate data on the server for any clients that support mTLS. So how to fix that? Easy, just use the first certificate from the array. That's exactly how Keycloak patched this vulnerability. It's a good example of how developers provide methods and interfaces that can be misunderstood or used incorrectly. Another common scenario for mTLS deployments is when TLS connection is terminated on the reverse proxy. In this case, the reverse proxy often checks the certificate and forwards it to a backend server as an additional header. In these slides, you can see how a typical Nginx configuration to enable mTLS. I've seen a number of systems like that. And in most cases, the backend servers behind Nginx do not perform additional validation, trusting the reverse proxy. This behavior is not exploitable straight away, but it's not ideal either. Why? Well, first of all, it means that the server in the local network, that any server in the local network can make a request with this header. So this network segment should be properly isolated from the traffic coming from outside. Additionally, if a backend or reverse proxy is affected by request smuggling, its exploitation becomes trivial. Over the past few years, we've seen a lot of request and header smuggling vulnerabilities, including the latest CVEs in Apache and Node.js. Be careful when implementing these scenarios and check the certificate signature on all servers if possible. All right, moving on to the next chapter, follow the chain where it leads you. In large systems, servers may not store all root and intermediate certificates locally, but use an external storage instead. RFC 4387 defines the concept of a certificate store, an interface you can use to lazily access the certificates during chain validation. These stores are implemented over different protocols, such as HTTP, LDAP, FTP, or SQL queries. The X509 format defines some certificate extensions that can contain information where to find the issuer and CA certificates. For instance, the Authority Information Access extension contains a URL pointing to the issuer's certificate. If this extension is used for validation, there is a high chance that you can exploit it to perform a SSRF attack. Also, subject, issuer, serial, and their alternative names can be used to construct SQL or LDAP queries, leaving option for injections attack. When certificate stores are in use, you want to think about these values as insertion points, similar to these ones we have in Verb Suite Intruder. And what's really good for attackers, all of these values can be used in queries before the signature is checked. To demonstrate an example of this vulnerability, we'll use LDAP cert store from the Bouncy Castle library. Bouncy Castle is one of the most popular libraries for the certificate validation in Java. Here is an example of how you can use this store to build and validate a certificate chain. Under the hood, Bouncy Castle uses the subject field from the certificate to build an LDAP query. The subject field is inserted into the filter and, as you can imagine, without any escaping. So, if the subject contains any special characters, it can change the syntax of the query. In most cases, it can be exploited as a blind LDAP query injection. Therefore, it could be possible to use this vulnerability to extract other fields from the LDAP directory. The exploitation is based on many factors, including whether the application exposes any errors, and it also depends on the structure of the LDAP directory. Anyway, whenever you incorporate user-supplied data into the LDAP query, special characters should be properly filtered. And that's exactly how this CV has been patched in the Bouncy Castle code. Next, we'll cover revocation. This controversial topic sparked many debates over the years. Similar to JSON Web Tokens, the beauty of certificate chains is that they can be trusted just based on the signature. But what happens if we need to revoke a certificate so it can no longer be used? The PKI specification addresses this problem by proposing a special store for revoked certificates that can be accessible via HTTP or LDAP protocols. Certificate verifiers can use two different methods, OSCP or CRL. Many developers believe that revocation checking is absolutely necessary, whereas others urge to avoid it for performance reasons or use offline revocation lists. Generally speaking, the store location can be hard-coded into the application or taken from the certificate itself. There are two certificate extensions used for that: Authority Information Access and CRL distribution points. Looking at from the hacker point of view, I think it's incredible that the location of the revocation server can be taken from the certificate. So if application takes URLs relying on extensions to make a revocation check, it can be abused for SSRF attacks. Sadly for attackers, this normally happens only after the signature checks, but in some cases, it's still exploitable. Moreover, the LDAP is also supported, at least in Java. Well, did I hear LDAP in Java? Yes. The standard Java library can use JNDI to access revocation locations under some settings. You can probably heard that in Java, unmarshalling an LDAP lookup response can lead to a remote code execution. A few years back, this problem was reported by Moritz Bechler, and remote code execution via revocation has been patched in GTK at least. You can check out his blog post for more details. In my research, I decided to check if Bouncy Castle library is also affected. It turns out that Bouncy Castle can be configured to use CRLDP extension and make calls to an LDAP server. At the same time, Bouncy Castle only fetches a specific attribute from the LDAP response and does not support references. So remote code execution is not possible there. At the same time, HTTP SSRF is still viable vector though. I also had a quick look at open source projects that support mTLS and perform revocation checking. One of these projects was APRIOCAS. It's another popular authentication server that is highly configurable. Administrators of APRIOCAS can enable the revocation check using the external LDAP server by specifying its address and password in the settings. If these settings are applied, APRIOCAS performs a revocation check for the certificate, fetching the address from the certificate's CRLDP extension, which is unsafe. I was afraid that this could lead to a remote code execution, but it turned out that APRIOCAS uses a custom library for LDAP connections, which does not support external code bases or object factories needed for the RCE. But when I tested this APRIOCAS, I noticed one interesting behavior. The server prefers LDAP URLs located inside the certificate instead of the one that is configured in settings. At the same time, API request still sends the passwords from settings. I quickly set a testing environment and send a self-signed certificate in the header. This certificate has CRLDP extension with LDAP URL pointing to a netcat listener. After sending this request to API request, I managed to receive a request to my netcat listener with the username and password leaked. After reporting this vulnerability, the application developers issued a fix within just 1 day. They patched it by clearing the login and password used for LDAP connection if the URL was taken from CRLDP extension. Therefore, the password leak is no longer possible. But I'd say in general, using URLs from the CRLDP extension is still dangerous, as it broadens the attack surface. All right, to summarize on attack section, when you develop an mTLS system or perform a security assessment, I strongly suggest: first, pay attention when extracting usernames from the mTLS chain, as the servers only verify the first certificate in the chain. Second, use certificate stores with caution, as it can lead to LDAP and SQL injections. And last but not least, certificate revocation can lead to SSRF or even to RCE in worst case. So it's advised to do the revocation check only after all other checks. That's it. Thank you for your attention. You can find the full write-up in our GitHub blog. Bye.